Learning objectives. In this chapter, the user would learn the following in detail. Requirements on Internet, streaming audio and video, access through web server, real-time streaming protocol RTSP, voice over IP, VoIP and Internet phone packet loss, end-to-end delay, delay jitter, fixed and adaptive playout, RTP, RTCP and SIP protocols. RTCP, Real-Time Transport Control Protocol RTCP. RTCP is the control protocol designed to work in conjunction with RTP. In an RTP session, participants periodically send RTCP packets to all the members in the same RTP session using IP multicast. RTCP packets contain sender and/or receiver reports that announce statistics such as number of packets sent, number of packets lost, and inter-arrival jitter. This function may be useful for adaptive applications that can use this feedback to send high or low quality data depending on the network congestion. Such applications will increase the compression ratio when there is little available bandwidth and will reduce the ratio, which will result in higher multimedia quality when there is more available bandwidth. RTCP provides a way to correlate and synchronize different media streams that have come from the same sender. When collisions of SSRC occur, it is necessary to change the SSCR value of a given stream. This is done using RTCP. In applications that involve separate multimedia streams, a common system clock is used for their synchronization. The system initiates the session, provides this function, and the RTCP messages enable all systems to use the same clock. Figure: Real-Time Transport Control Protocol. 5 types of RTCP packets that carry control information. RR, Receiver Report. Receiver reports are generated by participants that are not active senders. They contain reception quality feedback about data delivery, including the highest packets number received, the number of packets lost, inter-arrival jitter, and timestamps to calculate the round-trip delay between the sender and the receiver. SR, Sender Report. Sender reports are generated by active senders. In addition to the reception quality feedback, as in RR, they contain a sender information section providing information on intermedia synchronization, cumulative packet counters, and number of bytes sent. SDES, Source Description Items. They contain information to describe the sources. In RTP data packets, sources are identified by randomly generated 32-bit identifiers. These identifiers are not convenient for human users. RTCP SDES packets contain textual information called canonical names as globally unique identifiers of the session participants. It may include the user's name, telephone number, email address, and other information. By indicated end of participation. App, application-specific functions. These are intended for experimental use as new applications and new features are developed. RTP. Since most multimedia networking applications can make use of sequence numbers and timestamps, it is convenient to have a standardized packet structure that includes fields for audio-video data, sequence number, and timestamp, as well as other potentially useful fields. RTP is such a standard. RTP can be used for transporting common formats such as PCM, ACC, and MP3 for sound and MPEG and H.263 for video. It can also be used for transporting proprietary sound and video formats. Today, RTP enjoys widespread implementation in many products and research prototypes. It is also complementary to other important real-time interactive protocols such as SIP. RTP basics. RTP typically runs on top of UDP. The sending side encapsulates a media chunk within an RTP packet, then encapsulates the packet in a UDP segment and then hands the segment to IP. The receiving side extracts the RTP packet from the UDP segment, then extracts the media chunk from the RTP packet and then passes the chunk to the media player for decoding and rendering. The sending side precedes each chunk of the audio data with a RTP header that includes the type of audio encoding, a sequence number, and a timestamp. The RTP header is normally 12 bytes. The audio chunk along with the RTP header form the RTP packet. The RTP packet is then sent into the UDP socket interface. At the receiver side, the application receives the RTP packet from its socket interface. The application extracts the audio chunk from the RTP packet and uses the header fields of the RTP packet to properly decode and play back the audio chunk. If an application incorporates RTP instead of a proprietary scheme to provide payload type, sequence numbers, or timestamps, then the application will more easily interoperate with other network multimedia applications. RTP does not provide any mechanism to ensure timely delivery of data or provide other quality of service QoS guarantees. It does not even guarantee delivery of packets or prevent out of delivery of packets. Indeed, RTP encapsulation is seen only at the end systems. Routers do not distinguish between IP datagrams that carry RTP packets and IP datagrams that don't. RTP allows each source, for example, a camera or a microphone, to be assigned its own independent RTP stream of packets. However, many popular encoding techniques, including MPEG-1 and MPEG-2, bundle the audio-video into a single stream during the encoding process. When the audio and video are bundled by the encoder, then only one RTP stream is generated in each direction. RTP packets are not limited to unicast applications. They can also be sent over one-to-many and many-to-many multicast trees. For a many-to-many multicast session, all of the session senders and sources typically use the same multicast group for sending their RTP streams. RTP multicast streams belonging together, such as audio and video streams emanating from multiple senders in a video conference application, belong to an RTP session. RTP packet header fields. The four main RTP packet header fields are the payload type, sequence number, timestamp, source identifier fields. Figure RTP header fields. Payload type. The payload type field in the RTP packet is 7 bits long. For an audio stream, the payload type field is used to indicate the type of audio encoding that is being used. If a sender decides to change the encoding in the middle of a session, the sender can inform the receiver of the change through this payload type field. The sender may want to change the encoding in order to increase the audio quality or to decrease the RTP stream bitrate. For a video stream, the payload type is used to indicate the type of video encoding. The sender can change video encoding on the fly during a session. Sequence number field. The sequence number field is 16 bits long. The sequence number increments by 1 for each RTP packet sent and may be used by the receiver to detect packet loss and to restore packet sequence. For example, if the receiver side of the application receives a stream of RTP packets with a gap between sequence numbers 86 and 89, then the receiver knows that packets 87 and 88 are missing. The receiver can then attempt to conceal the lost data. Timestamp field. The timestamp field is 32 bits long. It reflects the stamping instant of the first byte in the RTP data packet. The receiver can use timestamps to remove packet jitter introduced in the network and to provide synchronous playout at the receiver. The timestamp is derived from a sampling clock at the sender. As an example, for the audio, the timestamp clock increments by 1 for each sampling period. If the audio application generates chunks consisting of 160 encoded samples, then the timestamp increases by 160 for each RTP packet when the source is active. The timestamp clock continues to increase at a constant rate even if the source is inactive. Synchronization Source Identifier SSRC. The SSRC field is 32 bits long. It identifies the source of the RTP stream. Typically, each stream in an RTP session has a distinct SSRC. The SSRC is not the IP address of the sender, but instead is a number that the source assigns randomly when the new stream is started. The probability that two streams get assigned the same SSRC is very small. Should this happen, the two sources pick a new SSRC value. RTSP. RTSP is an application-level protocol that enables control over the delivery of data with real-time properties over IP. Such control includes pausing playback, repositioning playback to future or past point of time, fast-forwarding, and rewinding playback. RTSP acts as a network remote control for multimedia servers. Sources of data include both live data feeds and stored clips. RTSP is a client-server multimedia presentation protocol. An RTSP session is no way tied to transport level protocol. During an RTSP session, an RTSP client may open and close many reliable transport connections to the server in order to issue RTSP requests. It may alternatively use a connectionless transport protocol such as UDP. RTSP is designed to work with lower level protocols like RTP and RSVP to provide a complete streaming service over the internet. The RTSP messages are sent out of band of the media stream. RTSP works for large audience multicast as well as single viewer unicast. RTSP establishes and controls streams of continuous audio and video media between the media servers and the clients. Operations supported by RTSP. Retrieval of media from the media server. The client can request a presentation description of HTTP or some other method. If the presentation is being multicasted, the presentation description contains the multicast address and ports to be used for continuous media. If the presentation is to be sent to the client only, the client provides the destination for security reasons. The client can also ask the server to set up a session to send the requested data. Invitation of a media server to a conference. A media server can be invited to join an existing conference either to play back media into the presentation or to record or a subset of the media in a presentation. Several parties in the conference may take turns pushing the remote control button. Adding media to an existing presentation. The server or the client can notify each other about any additional media becoming available. This is useful for live presentations. RTSP aims to provide the same services on streamed audio and video just as HTTP does for text and graphics. It is intentionally designed to have similar syntax and operations so that most extension mechanisms to HTTP can be added to RTSP. Each presentation and media stream in RTSP is defined by an RTSP URL. Difference between RTSP and HTTP. HTTP is a stateless protocol. RTSP has to maintain session states in order to correlate RTSP requests with a stream. HTTP is an asymmetric protocol where the client issues requests and the server responds, but in RTSP, both the media server and the client can issue requests. Services and operations supported by RTSP. Options. The client or the server informs the other party about the options it can accept. Describe. The client retrieves the description of a presentation or a media object identified by the request URL from the server. Announce. When sent from client to server, announce posts the description of a presentation or the media object identified by the request URL to a server. When sent from server to client, announce updates the session description in real time. Setup. The client asks the server to allocate resources for a stream and start an RTSP session. Play. The client asks the server to start sending data on a stream allocated via setup. Pause. The client temporarily halts the stream delivery without freeing server resources. Tear down. The client asks the server to stop the delivery of the specified stream and free the resources associated with it. Get parameter. Retrieves the value of a parameter of a presentation or a stream specified in the URL. Set parameter. Sets the value of a parameter of a presentation or a stream specified in the URL. Redirect. The server informs the clients that it must not connect to another server location. The mandatory location header indicates the URL that the client should connect to. Record. The client initiates recording a range of media data according to the presentation description. Requirements on Internet. The Internet was originally designed to support data communications. Most of the traffic initially included data such as emails and files. People in all corners of the world are currently using the Internet to watch movies and television shows on demand. People are not only watching Internet videos, they are using sites to upload and distribute their own user-generated content, becoming Internet video producers as well as consumers. Moreover, network applications allow people to not only to make telephone calls over the Internet, but to also enhance those calls with video and multi-person conferencing. We can safely predict that by the end of the current decade, almost all video distribution and voice conversations will take place end-to-end over the Internet, often to wireless devices connected to the Internet via 4G and Wi-Fi access networks. SIP. The Session Initiation Protocol (SIP) is an open and lightweight protocol that does the following. It provides mechanisms for establishing calls between a caller and a callee over an IP network. It allows the caller to notify the callee that it wants to start a call. It allows the participants to agree on media encodings. It also allows participants to end calls. It provides mechanisms for the caller to determine the current IP address of the callee. Users do not have a single fixed IP address because they may be assigned addresses dynamically using DHCP, and because they have multiple IP devices, each with a different IP address. It provides mechanisms for call management, such as adding new media streams during the call, changing the encoding during the call, inviting new participants during the call transfer, and call holding. Setting up a call to a known IP address. Example: Alice is at her PC and she wants to call Bob, who is also working at his PC. Alice's and Bob's PCs are both equipped with SIP-based software for making and receiving phone calls. Assuming that Alice knows the IP address of Bob's PC, a SIP session begins when Alice sends an invite message which resembles an HTTP request message. This invite message is sent over UDP to the well-known port 5060 for SIP. The invite message includes an identifier for Bob at 193.64.210.89, an indication of Alice's current IP address, an indication that Alice desires to receive audio, which is to be encoded in format AVP0, PCM encoded _law, and encapsulated in RTP, and an indication that she wants to receive the RTP packets on port 38060. After receiving Alice's invite message, Bob sends an SIP response message which resembles an HTTP response message. This response SIP message is also sent to SIP port 5060. Bob's response includes a 200 OK as well as an indication of his IP address, his desired encoding and packetization for reception, and his port number to which the audio packets should be sent. Alice and Bob are going to use different audio encoding mechanisms. Alice encodes her audio with GSM, whereas Bob encodes his audio with PCM law. After receiving Bob's response, Alice sends Bob an SIP acknowledgement message. After this SIP transaction, Bob and Alice can talk. Bob will encode and packetize the audio as requested and send the audio packets to port number 38060 at IP address 167.180.112.24. Alice will also encode and packetize the audio as requested and send the audio packets to port number 48753 at IP address 193.64.210.89. Key characteristics of SIP. SIP is an out-of-band protocol. The SIP messages are sent and received in sockets that are different from those used for sending and receiving the media data. The SIP messages themselves are ASCII readable and resemble HTTP messages. SIP requires all messages to be acknowledged that it can run over UDP or TCP. Figure: SIP call establishment when Alice knows Bob's IP address. SIP address. SIP addresses mostly to resemble an email address. SIP addresses can be included in web pages just as people's email address are included in web pages with the mail to URL. When the visitor clicks on the URL, the SIP application in the visitor's device is launched and an invite message is sent. SIP messages. Suppose that Alice wants to initiate a VoIP call to Bob, and this time Alice knows only Bob's SIP address, bob@domain.com, and does not know the IP address of the device that Bob is currently using. Then her message might look something like this. Invite SIP bob@domain.com SIP 2.0 via SIP 2.0 UDP 167.180.112.24 from SIP alice@huawei.com to SIP bob@domain.com. Call ID A2E3A@pigeon.huawei.com. Content type application/SDP. Content length 885. C is equal to in IP4 167.180.112.24. M is equal to audio 38060 RTP/AVP0. The invite line includes the SIP version, as does an HTTP request message. Whenever a SIP message passes through a SIP device, it attaches a via header which indicates the IP address of the device. Similar to an email message, the SIP message includes a from header line and a to header line. The message includes a call ID which uniquely identifies the call, similar to the message ID in email. It includes a content type header line which defines the format used to describe the content contained in the SIP message. It also includes a content length header line which provides the length in bytes of the content in the message. Finally, after a carriage return and a line feed, the message contains the content. Name translation and user location. IP addresses are dynamically assigned with DHCP. Example: suppose that Alice knows only Bob's email address, bob@domain.com, and that this same address is used for SIP-based calls. In this case, Alice needs to obtain the IP address of the device that the user bob@domain.com is currently using. To find this out, Alice creates an invite message that begins with invite bob@domain.com SIP 2.0 and sends this message to an SIP proxy. The proxy will respond with an SIP reply that might include the IP address of the device that bob@domain.com is currently using. Alternatively, the reply might include the IP address of Bob's voicemail box, or it might include a URL of a web page. Every SIP user has an associated registrar. Whenever a user launches a SIP application on a device, the application sends a SIP register message to the registrar, informing the registrar of its current IP address. Example: when Bob launches his SIP application on his PDA, the application would send a message along the lines of register SIP domain.com SIP 2.0 via SIP 2.0 UDP 193.64.210.89 from SIP bob@domain.com to SIP bob@domain.com expires 3600. The registrar is analogous to a DNS authoritative name server. The DNS server translates fixed host names to fixed IP addresses. The SIP registrar translates fixed human identifiers to dynamic IP addresses. Often, SIP registrars and SIP proxies are run on the same host. SIP, being a signaling protocol for initiating and ending calls in general, can be used for video conference calls as well as for text-based sessions. SIP has become a fundamental component in many instant messaging applications. Figure: session initiation involving SIP proxies and registrars. Streaming audio and video. We classify audio-video streaming into two categories: streaming stored audio-video Streaming live audio video. Streaming stored audio video. Pre-recorded videos are placed on servers and users send requests to the servers to view the videos on demand. Streaming stored video has three key distinguishing features. Streaming. In a streaming stored video application, the client typically begins video playout within a few seconds after it begins receiving the video from the server. This means that client will be playing out from one location in the video while at the same time receiving later parts of the video from the server. This technique, known as streaming, avoids having to download the entire video file and incurring a potentially long delay before playout begins. Interactivity. Because the media is pre-recorded, the user may pause, reposition forward, reposition backward, pass forward, and so on through the video content. The time from when the user makes such a request until the action manifests itself at the client should be less than a few seconds for acceptable responsiveness. Continuous playout. Once playout of the video begins, it should proceed according to the original timing of the recording. Therefore, data must be received from the server in time for its playout at the client. Otherwise, users experience video frame freezing when the client waits for the delayed frames, or frame skipping when the client skips over delayed frames. By far, the most important performance measure for streaming video is average throughput. In order to provide continuous playout, the network must provide an average throughput to the streaming application that is at least as large the bitrate of the video itself. For many streaming video applications, streaming live audio and video. This application allows the user to receive a live radio or television transmission, such as a live sporting event or an ongoing news event transmitted from any corner of the world. Live broadcast-like applications often have many users who receive the same audio-video program at the same time. The distribution of live audio-video to many receivers can be efficiently accomplished using the IP multicasting techniques. As with streaming stored multimedia, the network must provide each live multimedia flow with an average throughput that is larger than the video consumption rate. Because the event is live, delay can also be an issue, although the timing constraints are much less stringent than those for conversational voice. Techniques used for streaming live media: initial buffering delay, adaptive bandwidth use, and CDN distribution are similar to those for streaming stored media. Streaming stored video. For streaming stored video applications, pre-recorded videos are placed on servers and users send requests to these servers to view the videos on demand. Streaming video systems can be classified into three categories: UDP streaming, HTTP streaming, adaptive HTTP streaming. Although all three types of systems are used in practice, majority systems employ HTTP streaming and adaptive HTTP streaming. A common characteristic of all three forms of video streaming is the extensive use of client-side application buffering to mitigate the effects of varying end-to-end delays and varying amounts of available bandwidth between server and client. Advantages of client buffering. First, client-side buffering can absorb variations in server-to-client delay. If a particular piece of video data is delayed, as long as it arrives before the reserve of received but not yet played video is exhausted, this long delay will not be noticed. Second, if the server-to-client bandwidth briefly drops below the video consumption rate, a user can continue to enjoy continuous playback again as long as the client application buffer does not become completely drained. Client playout delay in video streaming, client-side buffering. UDP streaming. With UDP streaming, server transmits video at a rate that matches the client's video consumption rate by clocking out the video chunks over UDP at a steady rate. Since UDP does not employ a congestion control mechanism, the server can push packets into the network at the consumption rate of the video without the rate control restrictions of TCP. UDP streaming typically uses a small client-side buffer big enough to hold less than a second of a video. Before passing the video chunks to UDP, the server will encapsulate the video chunks within transport packets specially designed for transporting audio and video using the real-time transport protocol RTP. In addition to the server-to-client video stream, the client and server also maintain in parallel a separate control connection over which the client sends commands regarding session state changes. The real-time streaming protocol RTSP is an open protocol for such a control connection. Drawbacks of UDP. Due to the unpredictable and varying amount of available bandwidth between server and client, constant rate UDP streaming can fail to provide continuous playout. It requires a media control server such as an RTSP server to process client-to-server interactivity request and to track client state for each ongoing client session. This increases the overall cost and complexity of deploying a large-scale video on-demand system. Many firewalls are configured to block UDP traffic, preventing the users behind these firewalls from receiving UDP video. HTTP streaming. In HTTP streaming, the video is simply stored in an HTTP server as an ordinary file with a specific URL. When a user wants to see the video, the client establishes a TCP connection with the server and issues a HTTP GET request from the URL. The server then sends the video file within an HTTP response message as quickly as TCP congestion control and flow control will allow. On the client side, the bytes are collected in a client application buffer. Once the number of bytes in this buffer exceeds a predetermined threshold, the client application begins playback. Specifically, it periodically grabs video frames from the client application buffer, decompresses the frames, and displays them on the user screen. Packets can also be significantly delayed due to TCP's retransmission mechanism. The use of HTTP over TCP also allows the video to traverse firewalls and NATs more easily. Streaming over HTTP also obviates the need for a media control server such as an RTSP server, reducing the cost of a large-scale deployment over the internet. Prefetching video. Client-side buffering can be used to mitigate the effects of varying end-to-end delays and varying available bandwidth. For streaming stored video, the client can attempt to download the video at a rate higher than the consumption rate, thereby prefetching video frames that are to be consumed in the future. This prefetched video is naturally stored in the client application buffer. Such prefetching occurs naturally with TCP streaming since TCP's congestion avoidance mechanism will attempt to use all of the available bandwidth between server and client. Figure: streaming stored video over HTTP TCP. Analysis of video streaming. Let R denote the video consumption rate, the rate at which the client draws bits out of the client application buffer during playback. Let's assume that the server sends bits at a constant rate x whenever the client buffer is not full. Suppose at time t is equal to 0, the application buffer is empty and video begins arriving at the client application buffer. The amount of time required to build up q bits, the initial buffering delay, is q by x. If x less than r, then the client buffer will never become full. Eventually, the client buffer will empty out entirely, at which time the video will freeze on the screen while the client buffer waits another second to build up q bits of video. Thus, when the available rate in the network is less than the video rate, playout will alternate between periods of continuous playout and periods of freezing. When the available rate in the network is more than the video rate after the initial buffering delay, the user will enjoy continuous playout until the video ends. Early termination and repositioning the video. HTTP streaming systems often make use of the HTTP byte range header in the HTTP GET request message, which specifies the specific range of bytes the client currently wants to retrieve from the desired video. When the user repositions to a new position, the client sends a new HTTP request indicating with the byte range header from which byte in the file should the server send data. When the server receives the new HTTP request, it can forget about any earlier request and instead send bytes beginning with byte indicated in the byte range request. When a user repositions to a future point in the video or terminates the video early, some pre-fetched but not yet viewed data transmitted by the server will go unwatched, a waste of network bandwidth and server resources. This is significant wasted bandwidth in the internet due to early termination. For this reason, many streaming systems use only a moderate size client application buffer or will limit the amount of pre-fetched video using the byte range header in the HTTP requests. Adaptive streaming and Dash. In Dash, dynamic adaptive streaming over HTTP, Dash, the video is encoded into several different versions, with each version having a different bit rate and, correspondingly, a different quality level. Dash allows clients with different internet access rates to stream in video at different encoding rates. Clients with the low-speed internet connections can receive a low bitrate version, and clients with fiber connections can receive a high-quality version. Dash allows the client to adapt to the available bandwidth if the end-to-end bandwidth changes during the session. With Dash, each video version is stored in the HTTP server, each with a different URL. The HTTP server also has a manifest file which provides a URL for each version along with its bitrate. The client first requests the manifest file and learns about the various versions. The client then selects one chunk at a time by specifying a URL and a byte range in an HTTP GET request message for each chunk. While downloading chunks, the client also measures the received bandwidth and runs a rate determination algorithm to select the chunk to request next. Dash therefore allows the client to freely switch among different quality levels. By dynamically monitoring the available bandwidth and client buffer level and adjusting the transmission rate with version switching, Dash can often achieve continuous playout at the best possible quality level without frame freezing or skipping. Since the client, rather than the server, maintains the intelligence to determine which chunk to send next, the scheme also improves server-side scalability. Another benefit of this approach is that client can use the HTTP byte range request to precisely control the amount of prefetched video that it buffers locally. Each audio version has its own quality level and bitrate and has its own URL. In these implementations, the client dynamically selects both video and audio chunks and locally synchronizes audio and video playout. Content distribution networks. For an internet video company, the most straightforward approach to providing streaming video service is to build a single massive data center, store all of its videos in that data center, and stream the videos directly from the data center to clients worldwide. But there are three major problems with this approach. If the client is far from the data center, the server-to-client packets will cross many communication links and likely pass through many ISPs, with some of the ISPs possibly located on different continents. If one of these links provides a throughput that is less than the video consumption rate, the end-to-end throughput will also be below the consumption rate, resulting in annoying freezing delays for the user. A popular video will likely be sent many times over the same communication links. Not only does this waste network bandwidth, but the internet video company itself will be paying its provider ISP connected to the data center for sending the same by internet over and over again. A single data center represents a single point of failure. If the data center or its links to the internet goes down, it would not be able to distribute any video streams. In order to meet the challenge of distributing massive amounts of video data to users distributed around the world, almost all major video streaming companies make use of content distribution networks, CDNs. A CDN manages servers in multiple geographical distributed locations, stores copies of the videos in its servers, and attempts to direct each user request to a CDN location that will provide the best user experience. The CDN may be a private CDN that is owned by the content provider itself, or be a third-party CDN that distributes content on behalf of multiple content providers. CDNs typically adopt one of two different server placement philosophies. Enter deep. Enter deep into the access networks of the internet service providers by deploying server clusters in access ISPs all over the world. The goal is to get close to end users, thereby improving user perceived delay and throughput by decreasing the number of links and routers between the end user and the CDN cluster from which it receives content. Bring home. Bring the ISPs home by building large clusters at a smaller number of key locations and connecting these clusters using a private high-speed network. Instead of getting inside the access ISPs, these CDNs typically place each cluster at a location that is simultaneously near the POPs of many Tier 1 ISPs. Many CDNs do not push videos to their clusters, but instead use a simple pull strategy. If a client requests a video from a cluster that is not storing the video, then the cluster retrieves the video and stores a copy locally while streaming the video to the client at the same time. Similar to internet caches, when a cluster's storage becomes full, it removes videos that are not frequently requested. CDN operation. When a browser in a user's host is instructed to retrieve a specific video, the CDN must intercept the request so that it can 1. Determine a suitable CDN server cluster for that client at that time, and 2. To redirect the client's request to a server in that cluster. Suppose a content provider, NetCinema, employs the third-party CDN company, King CDN, to distribute its videos to its customer. On the NetCinema web pages, Each of its video is assigned a URL that includes the string video and a unique identifier for the video itself. 6 steps then as shown in. The user visits the web page at NetCinema. When the user clicks on the link http video.netcinema.com/6y7b23v, the user's host sends a DNS query for video.netcinema.com. The user's local DNS server, LDNS, relays the DNS query to an authoritative DNS server for NetCinema, which observes the string video in the hostname video.netcinema.com. To hand over the DNS query to KingCDN instead of returning an IP address, the NetCinema authoritative DNS server returns to the LDNS a hostname in the KingCDN's domain. From this point on, the DNS query enters into KingCDN's private DNS infrastructure. The user's LDNS then sends a second query, now for a1105.kingcdn.com, and KingCDN's DNS system eventually returns the IP addresses of KingCDN content server to the LDNS. It is thus here within the KingCDN's DNS system that the CDN server from which the client will receive its content is specified. The LDNS forwards the IP of the content serving CDN node to the user's host. Once the client receives the IP address for a KingCDN content server, it establishes a direct TCP connection with the server at that IP address and issues an HTTP GET request for the video. If dash is used, the server will first send to the client a manifest file with a list of URLs, one for each version of the video, and the client will dynamically select chunks from the different versions. Figure DNS redirects a user's request to a CDN server. Cluster selection strategies. Cluster selection strategy is a mechanism for dynamically directing clients to a server cluster or a data center within the CDN. Assign the client to the cluster that is geographically closest. For some clients, this solution may perform poorly since the geographically closest cluster may not be the closest cluster along the network path. Furthermore, a problem inherent with all DNS-based approaches is that some end users are configured to use remotely located LDNSs, in which case the LDNS location may be far from the client's location. This ignores the variation and available bandwidth over time of internet paths, always assigning the same cluster to a particular client. Perform periodic real-time measurements. In order to determine the best cluster for a client based on the current traffic conditions, CDNs can instead perform periodic real-time measurements of delay and loss performance between their clusters and clients. One drawback of this approach is that many LDNSs are configured to not respond to such probes. Use the characteristics of recent and ongoing traffic between the clients and CDN servers. The delay between a client and a cluster can be estimated by examining the gap between server-to-client (SYNAC) and client-to-server (ACK) during the TCP three-way handshake. Such solutions, however, require redirecting clients to possibly suboptimal clusters from time to time in order to measure the properties of paths to these clusters. Although only a small number of requests need to serve as probes, the selected clients can suffer significant performance degradation when receiving content. Use DNS query traffic to measure the delay between clients and clusters. Specifically, during the DNS phase, the client's LDNS can be occasionally detected to to different DNS authoritative servers installed at the various cluster locations, yielding DNS traffic that can then be measured between the LDNS and these cluster locations. In this scheme, the DNS servers continue to return the optimal cluster for the client so that delivery of videos and other web objects does not suffer. Use IP Anycast. The idea behind IP Anycast is to have the routers in the internet route the client's packets to the closest cluster as determined by BGP. Specifically, during the IP Anycast configuration stage, the CDN company assigns the same IP address to each of its clusters and uses standard BGP to advertise this IP address from each of the different cluster locations. When a BGP router receives multiple route advertisements from this same IP address, it treats these advertisements as providing different paths to the same physical location. Following standard operating procedures, the BGP router will then pick the best route to the IP address according to its local route selection mechanism. Figure using IP Anycast to route clients to closest CDN cluster. Voice over IP, VoIP, and Internet phone. Voice over IP. Real-time conversational voice over the Internet is often referred to as Internet telephony, since, for the user's perspective, it is similar to the traditional circuit-switched telephone service. It is also commonly called Voice over IP, VoIP. In this section, we describe the principles and protocols underlying VoIP. Conversational video is similar in many aspects to VoIP, except that it includes the video of the participants as well as their voices. Limitations of the best effort IP service. The Internet's Network Layer Protocol IP provides best effort service. A chunk and a special header discussed below are encapsulated in a UDP segment via a call to the socket interface. Thus, the number of bytes in a chunk is 20 milliseconds, 8000 bytes per second is equal to 160 bytes, and a UDP segment is sent every 20 milliseconds. If each packet makes it to the receiver with a constant end-to-end delay, then packets arrive at the receiver periodically every 20 milliseconds. In these ideal conditions, the receiver can simply play back each chunk as soon as it arrives. But, unfortunately, some packets can be lost and most packets will not have the same end-to-end delay even in a lightly congested internet. For this reason, the receiver must take more care in determining 1. When to play back a chunk, and 2. What to do with the missing chunk. Packet loss. The UDP segment is encapsulated in an IP datagram. As the datagram wanders through the network, it passes through router buffers, that is queues, while waiting for transmission on outbound links. It is possible that one or more of the buffers in the path from sender to receiver is full, in which case the arriving IP datagram may be discarded, never to arrive at the receiving application. Loss could be eliminated by sending the packets over TCP rather than over UDP. However, retransmission mechanisms are often considered unacceptable for conversational real-time audio applications such as VoIP because they increase end-to-end delay. Due to TCP congestion control, packet loss may result in a reduction of the TCP sender's transmission rate to a rate that is lower than the receiver's drain rate, possibly leading to buffer starvation. Packet loss rates between 1 and 20% can be tolerated, depending on how voice is encoded and transmitted and on how the loss is concealed at the receiver. End-to-end delay. End-to-end delay is the accumulation of transmission, processing and queuing delays in routers, propagation delays in links, and end system processing delays. For real-time conversational applications such as VoIP, end-to-end delays smaller than 150 milliseconds are not perceived by a human listener. Delays between 150 and 400 milliseconds can be acceptable but are not ideal, and delays exceeding 400 milliseconds can seriously hinder the interactivity in voice conversations. The receiving side of a VoIP application will typically disregard any packets that are delayed more than a certain threshold, for example, more than 400 milliseconds. Thus, packets that are delayed by more than the threshold are effectively lost. Delay. Jitter. A crucial component of end-to-end delay is the varying queue delays that a packet experiences in the network's router. Because of these varying delays, the time from when a packet is generated at the source until it is received at the receiver can fluctuate from packet to packet. This phenomena is called jitter. If the receiver ignores the presence of jitter and plays out chunks as soon as they arrive, then the resulting audio quality can easily become unintelligible at the receiver. Jitter can often be removed by using sequence numbers, timestamps, playout delay. Example: consider two consecutive packets in our VoIP application. The sender sends the second packet 20 milliseconds after sending the first packet. But at the receiver, the spacing between these packets can become greater than 20 milliseconds. To see this, suppose the first packet arrives at a nearly empty queue at a router, but just before the second packet arrives at the queue, a larger number of packets from other sources arrive at the same queue. Because the first packet experiences a small queuing delay and second packet suffers a large queuing delay at this router, the first and second packets become spaced by more than 20 milliseconds. The spacing between consecutive packets can also become less than 20 milliseconds. To see this, again consider two consecutive packets. Suppose the first packet joins the end of a queue with a large number of packets and the second packet arrives at the queue before this first packet is transmitted, before any packets from other sources arrive at the queue. In this case, our two packets find themselves one right after the other in the queue. If the time it takes to transmit a packet on the router's outbound link is less than 20 milliseconds, then the spacing between the first and second packets becomes less than 20 milliseconds. Removing jitter at the receiver for audio. The receiver attempts to provide periodic playout of voice chunks in the presence of random network jitter by combining the following two mechanisms. Prepending each chunk with the timestamp. The sender stamps each chunk with the time at which the chunk was generated. Delaying playout of chunks at the receiver. The playout delay of the received audio chunks must be long enough so that most of the packets are received before their scheduled playout times. This playout delay can either be fixed throughout the duration of the audio session or vary adaptively during the audio session lifetime. Fixed playout delay. With a fixed delay strategy, the receiver attempts to play out each chunk exactly q milliseconds after the chunk is generated. So, if a chunk is timestamped at the sender at time t, the receiver plays out the chunk at time t plus q, assuming the chunk has arrived by that time. Packets that arrived after the scheduled playout times are discarded and considered lost. VoIP can support delays up to about 400 milliseconds, although a more satisfying conversational experience is achieved with smaller values of Q. On the other hand, if Q is made much smaller than 400 milliseconds, then many packets may miss their scheduled playback times due to the network-induced packet jitter. The sender generates packets at regular intervals, say every 20 milliseconds. The first packet in this talk spurt is received at time R. The arrivals of subsequent packets are not evenly spaced due to the network jitter. For the first playout schedule, the fixed initial playout is set to P minus R. With this schedule, the fourth packet does not arrive by its scheduled playout time and the receiver considers it lost. For the second playout schedule, the fixed initial playout delay is set to P underscore minus R. For this schedule, all packets arrive before their scheduled playout times and there is therefore no loss. Figure: packet loss for different fixed playout delays. Adaptive playout delay. The natural way to deal with trade-off is to estimate the network delay and the variance of the network delay and to adjust the playout delay accordingly at the beginning of each talk spurt. This adaptive adjustment of playout delays at the beginning of the talk spurts will cause the sender's silent periods to be compressed and elongated. However, compression and elongation of silence by a small amount is not noticeable in speech. A generic algorithm that the receiver can use to adaptively adjust its playout delays. Ti is equal to the timestamp of the ith packet is equal to the time the packet was generated by the sender. Ri is equal to the time packet I is received by receiver. Pi is equal to the time packet I is played at receiver. The end-to-end network delay of the ith packets is Ri minus Ti. Due to network jitter, this delay will vary from packet to packet. Let Di denote an estimate of the average network delay upon reception of the ith packet. This estimate is constructed from the timestamps as follows. Di is equal to 1 minus u di minus 1 plus u into Ri minus Ti, where u is a fixed constant. Thus, Di is a smoothed average of the observed network delays R1 minus T1 to Ri minus Ti. The estimate places more weight on the recently observed network delays than on the observed network delays of the distant past. Let Vi denote an estimate of the average deviation of the delay from the estimated average delay. This estimate is also constructed from the timestamps. Vi is equal to 1 minus u into Vi minus 1 plus u into modulus of Ri minus Ti minus Di. The estimates Di and Vi are calculated from every packet received, although they are used only to determine the playout point for the first packet in any talk spurt. Having calculated the estimates, the receiver employs the following algorithm for the playout of packets. If the packet I is the first packet of a talk spurt, its playout time Pi is computed as Pi is equal to Ti plus Di plus kVi, where k is a positive constant. The purpose of the kVi term is to set the playout time far enough into the future so that only a small fraction of the arriving packets in the talk spurt will be lost due to late arrivals. The playout point for any subsequent packet in a talk spurt is computed as an offset from the point in time when the first packet in the talk spurt was played out. In particular, let Qi is equal to pi minus ti be the length of time from when the first packet in the talk spurt is generated until it is played out. If packet j also belongs to this talk spurt, it is played out at time pj is equal to tj plus qi. From the algorithm, the receiver can tell whether a packet is the first packet in the talk spurt. This can be done by examining the signal energy in each received packet. Recovering from packet loss. Schemes that attempt to preserve acceptable audio quality in the presence of packet loss are called loss recovery schemes. Packet loss definition in a broad sense. A packet is lost either if it never arrives at the receiver or if it arrives after its scheduled playout time. Retransmitting lost packets may not be feasible in a real-time conversational application such as VoIP. Indeed, retransmitting a packet that has missed its playout deadline serves absolutely no purpose. And retransmitting a packet that overflowed a router queue cannot normally be accomplished quickly enough. Because of these considerations, VoIP applications often use some type of loss anticipation scheme. Two types of loss anticipation schemes are forward error correction (FEC) interleaving. Forward error correction. The basic idea of FEC is to add redundant information to the original packet stream. For the cost of marginally increasing the transmission rate, the redundant information can be used to reconstruct approximations or exact versions of some of the lost packets. The first mechanism sends a redundant encoder chunk after every n chunks. The redundant chunk is obtained by exclusive Ring the n original chunks. In this manner, if any one packet of the group of n plus 1 packets is lost, the receiver can fully reconstruct the lost packet. But if two or more packets in a group are lost, the receiver cannot reconstruct the lost packets. Keeping n plus 1, the group size, small, a large fraction of the lost packets can be recovered when loss is not excessive. Smaller the group size, the greater the relative increase of the transmission rate. The transmission rate increases by a factor of 1 by n, so that if n is equal to 3, then the transmission rate increases by 33%. Increases the playout delay as the receiver must wait to receive the entire group of packets before it can begin playout. The second FEC mechanism is to send a low-resolution audio stream as the redundant information. For example, the sender might create a nominal audio stream and a corresponding low-resolution, low-bitrate audio stream. The low-bitrate stream is referred to as the redundant stream. The sender constructs the nth packet by taking the nth chunk from the nominal stream and appending to it the n-first chunk from the redundant stream. In this manner, whenever there is non-consecutive packet loss, the receiver can conceal the loss by playing out the low bitrate encoder chunk that arrives with the subsequent packet. Of course, low bitrate chunks give lower quality than the nominal chunks. However, a stream of mostly high-quality chunks, occasional low-quality chunks, and no missing chunks gives good overall audio quality. In this scheme, the receiver only has to receive 2 packets before playback, so that the increased playout delay is small. Furthermore, if the low bitrate encoding is much less than the nominal encoding, then the marginal increase in the transmission rate will be small. In order to cope with consecutive loss, we can use a simple variation. Instead of appending just the n-first low bit rate chunk to the nth nominal chunk, the sender can append the n-first and n-second low bitrate chunk, or append the n-first and n-third low bitrate chunk, and so on. By appending more low bitrate chunks at each nominal chunk, the audio quality at the receiver becomes acceptable for a wider variety of harsh best effort environments. On the other hand, the additional chunks increase the transmission bandwidth and the playout delay. Interleaving. As an alternative to redundant transmission, a VoIP application can send interleaved audio. The sender resequences units of audio data before transmission so that originally adjacent units are separated by a certain distance in the transmitted stream. Interleaving can mitigate the effect of packet losses. The loss of a single packet from an interleaved stream results in multiple small gaps in reconstructed stream as opposed to the single large gap that would occur in a non-interleaved stream. Interleaving can significantly improve the perceived quality of an audio stream. It also has low overhead. A disadvantage of interleaving is that it increases latency. This limits its use for conversational applications such as VoIP. It can perform well for streaming stored audio. A major disadvantage of interleaving is that it does not increase the bandwidth requirements of the stream. Figure: piggybacking lower quality redundant information. Figure: sending interleaved audio. Error concealment. Error concealment schemes attempt to produce a replacement for a lost packet that is similar to the original. This is possible since audio signals, and in particular speech, exhibit large amounts of short-term self-similarity. As such, these techniques work for relatively small loss rates less than 15% and for small packets 4 to 40 milliseconds. When the loss length approaches the length of a phoneme 5 to 100 milliseconds, these techniques break down since whole phonemes may be missed by the listener. Perhaps the simplest form of receiver-based recovery is packet repetition. Packet repetition replaces lost packets with copies of the packets that arrived immediately before the loss. It has low computational complexity and performs reasonably well. Another form of receiver-based recovery is interpolation, which uses audio before and after the loss to interpolate a suitable packet to cover the loss. Interpolation performs somewhat better than packet repetition but is significantly more computationally intensive. Conclusion. In this chapter, we have covered the following in detail: requirements on Internet, streaming audio and video, access through web server, real-time streaming protocol RTSP, voice over IP, VoIP, and Internet phone packet loss, end-to-end delay, delay jitter, fixed and adaptive playout, RTP, RTCP, and SIP protocols.